In the grand theater of the universe, few objects capture human imagination as powerfully as black holes. They are often called cosmic monsters, regions of space where gravity is so strong that nothing, not even light, can escape. The idea itself sounds like science fiction, yet black holes are not only real, they are central players in the evolution of galaxies and the destiny of stars. Black holes challenge everything we think we know about physics. They stretch Einstein's general theory of relativity to its limits and demand answers from quantum mechanics. For decades, scientists have asked, what happens at the heart of a black hole? Do they destroy information? Could they be gateways to other universes? To understand why black holes fascinate us so deeply, we must first explore how they form, what types exist, and why they may hold the key to understanding the very fabric of reality. At its core, a black hole is a region of spacetime where gravity has become so intense that escape velocity exceeds the speed of light. Escape velocity is the speed needed to break free from a celestial body's gravitational pull. For Earth, it's about 11 kilometers per second. For the Sun, it's about 617 kilometers per second. But inside a black hole's boundary, even light moving at 300,000 kilometers per second cannot escape. The boundary around a black hole is called the event horizon. Once something crosses this point, it is lost forever. Not even information can get back out? That's why black holes appear black. They emit no light, only devouring everything that strays too close. At the very center of a black hole lies the singularity, a point of infinite density and zero volume, where the known laws of physics break down. Whether singularities truly exist or are just mathematical illusions remains one of the greatest unsolved mysteries in science. Most black holes are born in the fiery deaths of massive stars. When a star many times more massive than our Sun exhausts its nuclear fuel, its core collapses under gravity. If the mass is high enough, no known force can stop the collapse, and a black hole is formed. The steps look like this. 1. Massive star burns hydrogen into helium for millions of years. 2. Supernova explosion gives when fuel runs out, the star collapses and outer layers explode. 3. Core collapse gives if the remaining mass is greater than about 3 solar masses, gravity overwhelms all forces. 4. Black hole gives the core collapses into a singularity surrounded by an event horizon. But black holes can form in other ways too. Primordial black holes may have formed in the early universe due to extreme density fluctuations. Supermassive black holes might grow by swallowing stars, gas, and other black holes over billions of years. Not all black holes are the same. Scientists classify them based on size and formation. A stellar mass black holes form from collapsing massive stars, range from about 3 to 100 times the Sun's mass. Many are detected in binary systems where they pull gas from a companion star, be intermediate mass black holes. Between 100 and 100,000 solar masses, harder to detect but may form in dense star clusters. They may act as the missing link between stellar and supermassive black holes. See supermassive black holes, found at the centers of galaxies, including our own Milky Way. Mass ranges from millions to billions of suns. Example, Sagittarius A** at the Milky Way's center has a mass of about 4 million suns. They may regulate galaxy formation and growth. D. Primordial black holes. Hypothetical tiny black holes formed soon after the Big Bang. Could be as small as an atom yet as massive as a mountain. Some scientists propose they may even make up part of the universe's dark matter. The most famous feature of a black hole is the event horizon. This is the invisible surface surrounding the black hole where escape velocity equals the speed of light. Anything crossing it, gas, dust, stars, even photons, can never return. For a black hole with the mass of our Sun, the event horizon would be just 3 kilometers across. For Sagittarius A**, the supermassive black hole at our galaxy's core, the event horizon is about 24 million kilometers wide. The event horizon acts like a one-way door. It does not suck matter in from afar like a vacuum cleaner, but anything that comes too close will inevitably fall inside. Interestingly, if you were to fall toward a black hole, an outside observer would see you slow down, redshift, and freeze at the event horizon, never quite crossing. But from your perspective, you would fall right through without noticing the horizon at all until spaghettification tidal stretching tears you apart. At the very core lies the singularity. According to Einstein's relativity, this is a point of infinite density where space and time collapse into nothing. But infinities are usually signs that a theory has reached its limits. Physicists suspect that at the singularity, quantum gravity, a yet known theory combining relativity and quantum mechanics, will replace our current laws. Until we discover it, the true nature of singularities remains hidden. Some ideas suggest singularities might not exist as points, but as quantum structures, fuzzballs, or even gateways to other universes. These are speculative but fascinating possibilities. One of the strangest predictions of Einstein's general theory of relativity is that time flows differently depending on gravity. The stronger the gravity, the slower time passes compared to regions of weaker gravity. This effect is called gravitational time dilation. Near a black hole, gravity is unimaginably strong. This means that for an observer near the event horizon, time moves much more slowly relative to someone far away. For example, imagine an astronaut hovering near a black hole's event horizon while their twin remains safely on Earth. If the astronaut spends just a few hours near the black hole, centuries might pass on Earth. When the astronaut returns, they would find themselves far in the future while having aged only a little. This idea was powerfully illustrated in the movie Interstellar, where a planet orbiting near a supermassive black hole experienced such extreme time dilation that 1 hour on the surface equaled 7 years in orbit. While dramatized, it's based on real physics. Approaching a black hole is not only a journey through warp time, but also through destructive gravity. The immense gravitational pull creates tidal forces differences in gravity between different parts of your body. If you fall feet first, gravity on your feet is much stronger than on your head. Your body stretches like spaghetti while being squeezed sideways. Eventually, you're torn apart in a process nicknamed spaghettification. For stellar mass black holes, spaghettification happens well before reaching the event horizon. For supermassive black holes, you could cross the event horizon without noticing tidal effects until you get much deeper inside. Black holes may be invisible, but the matter around them often glows brilliantly. As gas and dust spiral into a black hole, they form a rotating accretion disk. Friction within the disk heats the gas to millions of degrees. This produces powerful X-rays and gamma rays detectable by telescopes. Accretion disks are among the brightest objects in the universe despite forming around the darkest ones. In fact, the brightest objects we've ever observed, called quasars, are powered by supermassive black holes feeding on huge amounts of matter. A single quasar can outshine an entire galaxy with trillions of stars. Some black holes launch enormous jets of plasma shooting out at nearly the speed of light. These jets can extend for hundreds of thousands of light years. How do they form? As the accretion disk rotates, twisted magnetic fields accelerate particles outward along the black hole's poles. These relativistic jets can regulate star formation in galaxies, influencing cosmic evolution. Astronomers have observed galaxies with black hole jets so powerful they carve holes in intergalactic gas, shaping the structure of the universe itself. Discovered in the 1960s, quasars looked like faint stars but emitted more energy than entire galaxies. Today, we know they are supermassive black holes feeding at extreme rates. The farthest quasars we've observed date back to when the universe was less than 1 billion years old. This tells us that black holes and galaxies grew rapidly after the Big Bang. Studying quasars helps scientists understand the early universe and the role black holes played in shaping it. For decades, black holes remained theoretical. But in 2019, humanity achieved a milestone, the first direct image of a black hole. Using a global network of radio telescopes called the Event Horizon Telescope (EHT), scientists imaged the supermassive black hole in galaxy M87. The picture showed a glowing ring of hot gas around a dark shadow, the silhouette of the event horizon. In 2022, the HT captured an image of Sagittarius A*, the black hole at the center of our Milky Way. These observations confirmed decades of theory and gave humanity its first glimpse of the point of no return. For a long time, black holes were thought to be completely dark, swallowing everything without giving anything back. But in 1974, physicist Stephen Hawking made a revolutionary discovery: black holes can actually emit radiation. This happens because of quantum effects near the event horizon. In empty space, particle-antiparticle pairs constantly pop in and out of existence. Normally, they annihilate each other instantly. But near an event horizon, one particle may fall into the black hole while the other escapes. To an outside observer, it looks like the black hole is radiating energy. This is called Hawking radiation. The energy for this radiation comes from the black hole itself, meaning that black holes slowly lose mass over time. For stellar and supermassive black holes, the radiation is tiny and undetectable. But for very small black holes, Hawking radiation could be enormous, eventually leading to their complete evaporation. Hawking's theory implies that black holes are not eternal. Over incredibly long time scales, they shrink and disappear. A black hole the mass of our Sun would take about 10 years to evaporate. Supermassive black holes could last up to 10 years. In the far future, when stars burn out and galaxies fade, black holes may be the last surviving objects in the universe. As they evaporate, black holes would release a final burst of radiation, possibly an enormous gamma-ray explosion. Thus, in a strange twist, the darkest objects in the universe may end their lives in brilliant flashes of light. In 2015, scientists achieved another milestone: the first detection of gravitational waves ripples in spacetime predicted by Einstein 100 years earlier. These waves were created when the black holes collided and merged about 1.3 billion years ago. The collision released more energy in a fraction of a second than all the stars in the universe combined. The LIGO and Virgo observatories detected the stretching and squeezing of spacetime caused by the waves. Since then, dozens of black hole mergers have been detected, opening a new era of gravitational wave astronomy. This allows us to hear black holes colliding, something once thought impossible. Black holes don't just destroy, they also create. Evidence suggests that supermassive black holes shape the galaxies around them. Jets and winds from active black holes regulate star formation. If a black hole feeds too rapidly, it can blow gas out of a galaxy, stopping new stars from forming. If it feeds moderately, it can stir and heat gas, encouraging new generations of stars. In this way, black holes act as cosmic thermostats, balancing the growth of galaxies. Some scientists even propose that galaxies and their central black holes co-evolve, growing together over billions of years. One of the greatest mysteries of physics is the black hole information paradox. According to quantum mechanics, information about particles can never be destroyed. But if something falls into a black hole and the black hole later evaporates, where does that information go? Does it vanish forever, violating quantum laws? Or is it somehow encoded in the Hawking radiation? This paradox has puzzled scientists for decades. Recent theories suggest that information may be preserved in subtle quantum correlations at the event horizon, but no final answer exists yet. Solving this mystery may require a new theory that unites quantum mechanics with gravity, a theory of everything. Because black holes warp spacetime so extremely, many have speculated they might serve as gateways to other universes or distant regions of our own. Some solutions to Einstein's equations suggest the existence of wormholes, tunnels through spacetime. In theory, a black hole could be connected to a white hole, an object that only emits matter. However, such structures would be unstable and collapse quickly. While wormholes remain speculative, they are a favorite of science fiction, fueling stories from Interstellar to Star Trek. Since black holes emit no light, astronomers can't see them directly. Instead, they detect black holes by observing their effects on nearby matter. 1. Binary star systems. If a visible star orbits an invisible companion and the companion's gravity is too strong to be explained by a neutron star, it is likely a black hole. Example, Cygnus X1, the first confirmed stellar black hole. 2. Accretion disks. Gas falling into a black hole emits powerful X-rays. Telescopes like Chandra X-ray Observatory detect these signals. 3. Gravitational waves. Black hole mergers create ripples in spacetime, detected by LIGO and Virgo. 4. Imaging the shadow. The Event Horizon Telescope captures the silhouette of black holes against glowing gas, as with M87* and Sagittarius A*. Thus, while black holes are invisible, their footprints are unmistakable. Black holes often capture the public imagination, but not all ideas are accurate. Myth: black holes roam the galaxy, sucking everything in. Reality: they only pull objects that come close, just like stars do with gravity. Myth: black holes are portals we can travel through. Reality: current physics says falling into a black hole means destruction, not transport. Myth: the LHC Large Hadron Collider might create a black hole that swallows Earth. Reality: even if microscopic black holes were produced, they would evaporate instantly due to Hawking radiation. Black holes are fascinating, but not apocalyptic monsters lurking to consume us. We are living in a golden age of black hole discovery. In the coming decades, we expect major breakthroughs. Next-generation telescopes, instruments like the James Webb Space Telescope JWST and future X-ray observatories will study black holes in unprecedented detail. Gravitational wave astronomy. The LISA Mission Laser Interferometer Space Antenna will detect low-frequency waves, revealing mergers of supermassive black holes. Quantum gravity. Solving the information paradox may lead to a new theory uniting relativity and quantum mechanics. Primordial black holes and dark matter. If primordial black holes exist, they might explain mysterious dark matter. Detecting them could rewrite cosmology. Simulations and AI. Advanced computer models powered by AI will simulate accretion disks, jet formation, and black hole growth with stunning accuracy. Black holes may even play a role in the universe's ultimate destiny. In the Stelliferous era, the current age, stars are still forming and black holes are growing. In the degenerate era, trillions of years from now, stars will fade, leaving black holes as the dominant cosmic objects. In the black hole era, black holes themselves will evaporate through Hawking radiation. Finally, in the dark era, only radiation and elementary particles will remain. Thus, black holes may be both the last guardians of the cosmos and the final fireworks of a dying universe. Black holes force us to confront deep questions. Is reality fundamentally continuous or quantum? Can information truly be destroyed? Are black holes gateways to other universes or dead ends of physics? To study black holes is to study the boundaries of knowledge itself. They remind us that the universe is far stranger and richer than human imagination often dares to believe. Black holes are not just cosmic vacuum cleaners, they are laboratories for the universe's most extreme physics. They shape galaxies, forge quasars, warp time, and whisper secrets about quantum gravity. From stellar deaths to galactic giants, from gravitational waves to Hawking radiation, black holes sit at the crossroads of relativity, quantum mechanics, and cosmology. One day, by solving their mysteries, we may unlock the deepest truths of existence. Until then, they remain the most haunting and fascinating enigmas in the night sky's silent shadows, glowing with the secrets of the universe. As we reach the end of this journey into the heart of darkness, one truth stands out: black holes are not just cosmic monsters, they are cosmic teachers. They challenge our understanding of physics, they reshape galaxies, and they remind us that the universe still holds secrets far beyond our imagination. Think about it: objects born in the fiery deaths of stars can warp time, bend light, and create ripples in the very fabric of space-time. They may one day evaporate in bursts of Hawking radiation, or perhaps even reveal pathways to new dimensions. Every discovery about black holes is not just about the cosmos, it is about us, our curiosity, and our place in this vast universe. We used to fear black holes as destroyers. Now, we see them as laboratories of nature, pushing the boundaries of what we know. They are the dark hearts of galaxies, yet from their chaos, new order arises. They whisper that the universe is stranger and more beautiful than we dare to believe. So, the next time you look at the night sky, remember, somewhere out there, a black hole is bending reality itself, a silent reminder that the cosmos is both terrifying and magnificent. If this journey through the mysteries of black holes inspired you, don't forget to like this video, share it with friends, and subscribe for more explorations into the wonders of space science. Together, we'll continue traveling to the edge of knowledge, where science meets imagination and curiosity lights the way. Thank you for watching, and until next time, stay curious and keep looking up. In the silence of the cosmos, where stars are born and galaxies collide, there lie shadows, black holes, the dark hearts of creation. They bend light, they stretch time. They devour worlds, and yet they give us answers. From the death of stars to the birth of quasars. From ripples in spacetime to the echoes of eternity. Black holes remind us the universe is not an empty void, but a living mystery, endless and profound.